So I was last spring on sabbatical to Tanzania, where I had an opportunity to work some more on a project that I started working on back in 2006. I'm still working on today, and Brian's the latest recruit to the HALI Project. So I thought today we'd just go through some slides, talk about the story of the HALI Project and kind of what we're trying to do around disease modeling. So this is the title of my Fulbright grant that supports this work, or supported this work. Transdisciplinary disease modeling interventions at this Human-Livestock-Wildlife Interface in Semi-Arid ecosystems of East Africa. So I want to talk more today just about the context of this work, because I think it's more interesting than the nitty-gritty modeling stuff. And then towards the end I can discuss a bit of some of the preliminary modeling work that Brian and I are doing, always with the helpful hands of Gary in the background, helping the Aries model work. But these are all the partners on this. The initial push of this project was funded by one of these collaborative support research programs by USAID. A new CRIS program is supporting the modeling work on this livestock and climate change program. All the partners on this grant is really being led by UC Davis, our partners at UC Davis, the Wildlife Health Center there. And GUND is a partner on the ecological economic side of things, and we've really driven the social science and the survey work and the focus groups and all of that kind of, really the people side of the project. We're recently working with Colorado State University, who've done some really interesting agent-based modeling around pastoralists that we're trying to incorporate into this work. And our strong local partner is Sokoine University of Agriculture in Tanzania, which is where I was for my sabbatical. So we'll just walk through these four things today. I want to talk a bit about the Human-Livestock-Wildlife Interface and the context of this particular case of the Ruaha landscape of Tanzania, the kind of emergence of this stakeholder research partnership that I've been a part of since 2006, really started in 2004, 2005. Briefly, this kind of components of the HALI project. And then we'll get to this last piece, which is the newest part of this project, is this transdisciplinary disease modeling, which would be great to discuss because I think there are tons of opportunities for GUND to work around that interface of ecosystems and human and animal health. Some of these partnerships are right here on the university, and we're not taking advantage of them. And having Taylor here now, he's into some networks that I think this kind of work could be really ramped up at the GUND Institute. So this is the context of our work. This interface between people, domesticated animals, livestock, and wildlife. This interface is really sort of concerned with, there are huge land use changes around the world, population pressures, et cetera, et cetera. And this is really kind of magnifying this interface, or the contact between people, their livestock, as people and animals sort of live in more and more cramped quarters, and then interactions with wildlife. This magnification of this contact really is responsible for what we're seeing as sort of enhanced flows of pathogens, and that's really at the center of this is a concern with what are called zoonotic disease, or disease that jumps between animal species. This of course means health risks to humans, to livestock, to wildlife, as these diseases are passed back and forth. And then this puts further pressure on livelihoods, which then tends to reinforce the whole thing around we go again, right? Land use change, population growth, etc. So this is that classic vicious cycle that many of us study here at the GUND Institute. The majority of emerging infectious diseases are, in fact, in people are zoonotic. Usually we're most concerned when they pass to us, but there's a lot of concern around wildlife and in protected areas getting diseases from people or from livestock as well. So it's not just solely the human piece of the transmission that we're concerned with. Roughly, best guess, 75% of emerging zoonoses have wildlife origins. So we really have to think strong about kind of where these interfaces are occurring and where the disease reservoirs are, and what are the conditions and the kind of re-emergence in some cases of infectious disease or emergence of new infectious disease that we hadn't even thought about. There are many diseases out there that have been studied at this kind of interface, and we've started to tease out, many cases anecdotally, in some cases we're starting to get some research behind understanding how anthropogenic activities are driving these interfaces. So there's work on Nipah virus, SARS, Ebola. There's some classic examples, rabies being a big one, about this interface between people and other animals. And I think one of the most interesting pieces of the work that we're doing is kind of confirming that a lot of this, where we're most concerned about this interface is on the fringes of protected areas. Average annual population growth in places like where I'm working in East Africa are amongst the highest in buffers to protected areas. And this is for a lot of reasons, but basically a long history of drawing a circle on a map and kicking everybody out, right? So then you get people on the edges. These protected areas tend to be the last bastions of, you know, wood and meat and water, and so you get a lot of people and communities that are being developed around these protected areas in order to access those, what we call ecosystem services. There's also, these are gateway communities, so all the tourism activities that happen in those protected areas. So we're seeing huge population pressures around these little islands of conservation in places like Africa, Latin America, Asia, you know, even in the US and Western countries, from this legacy of non-integrated conservation, right? Just the draw a circle on a map, kick everybody out. We've got our island. That's the context of where we're working in Tanzania. So Tanzania is in East Africa, south of Kenya. Certainly one of the more well-known countries for wildlife tourism, wildlife hunting, those kinds of pressures and tourism activities. Where we're working in particular is in the Ruaha landscape, which is part of this larger Rufiji River water basin. It's a big piece of the landscape of Tanzania in general. Very important water basin in Tanzania. We're working in kind of what are called the Southern Highlands and in the Ruaha landscape, which, if you take together all the game reserves, the national park itself, and other protected areas in this landscape, it makes it the largest protected area in all of Tanzania. Although it gets far less attention than Serengeti and Ngorongoro Crater and all of those more popular places. This is really kind of the jewel of what's come to be known as the Southern Cirque in Tanzania. Great place to go visit because tourists just haven't really discovered it yet. And where we're really working is at this interface. So this is one of these experiments in a village-controlled wildlife management area. So the park boundary really stops at the Great Ruaha River, and this is the centerpiece to the conservation efforts that are going on. This game reserve actually was recently gazetted and now included in the national park, and then there are other game reserves up here where hunting is allowed. This is village-controlled area, and then you have 21 villages that we're working with that are just outside the park boundary. Classic place for this kind of interface that we're worried about. You've got wildlife, hunting, village lands, and this interface between people, livestock, and wildlife populations. This is an important landscape. It has all the classic conservation significance. It's a huge area for elephants, a huge corridor for elephants moving north-south in East Africa. Has the third largest population of wild dogs, which is a really threatened and endangered species in Africa. Lots of endemic species, all the classic conservation significance. This landscape is dominated by pastoralists, and so the resources are quite significant for rural livelihoods. It's in some ways the breadbasket, or really the rice basket for all of Tanzania. About 60% of the rice grown in Tanzania comes from this landscape. It's also really important for national development. So all the water that's generated in these highlands feeds this Ruaha river systems, runs 2 big hydro plants that produces 70% of the country's electricity. So all of the kind of industrial development and all of the development in the cities, but the big city, Dar es Salaam on the coast, are really, in a sense, sort of dependent on these upland communities. So the story here, and what makes it of real interest for trying to do research around these disease interfaces, is there's been a pretty substantial shock to the system in recent times. Lots of, this was according to World Bank types, a real underdeveloped area of the country in the 70s and 80s. So there's a lot of interest in pouring a lot of funds in there, developing it for rice irrigation, irrigated agriculture in general, dam development. And it's kind of one of those classic stories of unintended consequences, right? So we were diverting water in a semi-arid landscape that has that seasonality to it, this classic kind of East African seasonality between wet and dry season. Irrigating for rice all throughout the dry season, which has caused some substantial problems. And took a river that used to flow year-round pre-1993 and started to dry it up for longer and longer periods of time. So by the time we started working there in 2005, the Ruaha River, the main stem of the river, was experiencing a drying of upwards of 119 days. And it's been as high as 140 days since. So it used to run year-round. Now in a fairly short period of time, now drying upwards of 120, 130, 140 days a year.
Because of withdrawals, not because of climate change?
Partly. So one of the projects that we're working on now is to tease out that climate change signal, but this is mostly, this has happened so fast and so quickly because of upstream withdrawals. And that's part of the story that I'll get into in the next slide. Two principal reasons. The first being withdrawals, and so, big development projects go in there and irrigate an area. One of those unintended consequences was nice cement-lined ditches leading from the river to the irrigated rice paddies, bringing water from the river to the rice paddies, but then earth-lined ditches going from the rice paddies back to the river. And so what happened was just classic, tragedy of commons kind of thing, and folks were tapping into those earth-lined ditches. And some of the work by the Wildlife Conservation Society was to show the actual extent of flooding versus the presumed extent of flooding. So very sort of inefficient uses of water have in part led to the drying, and then irrigated agriculture in the dry season is probably never a good idea when you're talking about feeding the entire river. This put some pressures on those pastoralist communities, the drying of the main stem of the river. So they're trying to water their animals throughout the year. This drying also tended to open up the wetland areas, and the wetlands and systems like this act as those sponges, right, that soak up all the water, provide that flood regulation in the wet season when it's raining a lot, and then let that water just slowly trickle out through the dry season, and that becomes the source for a river to flow year-round. Well, very high cattle density along the Ruaha River, and folks started bringing their cattle more and more into the wetland areas during the dry season, and just hammered them, and really sort of affected that service that these wetlands were providing during the dry season. So it was kind of a 1-2 punch. Irrigation, inefficient irrigation, drying of the river, opening of the wetlands, in come the pastoralists, nail the wetlands even farther, and we're getting longer and longer and longer and longer dry periods to worry about.
And the power dams are downstream from here? 2
big power dams downstream, yeah, and if you're worried about the water issues downstream, there's certainly some inefficiencies to think about with the hydroelectric as well. The upper dam was never built with hydro in mind, and so they're spilling way more water than they need. So all of those kinds of issues are happening downstream as well. But yeah, this was all leading to by the late 90s and into when we started working there in 2005, 2006, longer and longer blackouts for the country. So now we've gone from a fairly localized issue to a regional issue, now to a national issue, and that's, as you can guess, when that really got the policymakers' attention, right? When their office in the city doesn't have any electricity. Now it's like, uh-oh, we've got a water problem. Pastoralists are way down on the totem pole in terms of power and influence in a country like Tanzania. So just some more parts of the stories. These are these really important and heathful wetlands. All of the rice irrigation was happening kind of upstream from the wetlands. Drying up the source, drying up the wetlands. Here are all the villages that were working. In come the pastoralists into the wetlands, hammer it even more. 91, the extent of the wetlands looks like this. By 2000, something like this. By 2006, shrunk still. They've since gazetted the wetlands. They've included them as part of the national park, much stronger restrictions. Before it was just a game reserve. Literally there were villages inside the game reserve. They've now been forcibly removed. This is when the city kind of, politicians got really concerned when the lights go off. And so now this is part of the national park. Classic kind of draw a circle on the map, kick everybody out. They're seeing some recovery of the wetlands and maybe some recovery of some of those flows from the wetlands, but they haven't adequately dealt with the upstream uses from agriculture. That one is still who do have political power, the big rice farms. The wildlife part of the story is, that main stem is really where the action is for the park and the tourists and the lodges. And you want to see animals in the Ruaha National Park, you do a drive along the river. And so we've got a lot of evidence that we're seeing a collapse first and foremost of the real water dependent species. Hippos, African buffalo, everything that needs water to get, big sources of water to get through the dry season. So you can see some of the work by the Wildlife Conservation Society seeing a trend of a collapse of the African buffalo range in this part of the river, which is that main border of the park with the village lands. So stress, water stress, climate stress. With or without climate change, it's a great case study for climate change, because you can imagine, if the models are showing greater variability or greater stress, here's a case over a 2-decade period of a before and after, right? Before the river's running and after it's not, and what are the mitigation attempts being tried, what are the adaptation attempts being tried, what are the interventions that we could imagine at this kind of landscape level. So downstream, the first reservoir that you hit is the Intera Reservoir. Here's a snapshot of that reservoir in '84, and by 2006 when we started working, February, so really very tail end of that dry season into the start of the wet season. You can see the extent of that reservoir is shrunk substantially. So, income. Some folks from the U.S. and from Sokoine University of Agriculture and the Wildlife Conservation Society, and a whole history of water projects that have happened in this region throughout the 80s and 90s, most around agriculture and using water efficiently. The wildlife groups start to get very interested. WWF has a big presence there, as does WCS, as does Conservation International, all the classic groups are being driven by the kind of impact on the park. A lot of the development groups are interested in the impact on the pastoralists. There's a tension between water for farms versus water for national development for power. All the classic things of what's going on here. So The early work was so this is a local veterinarian looking very confused after one of these classic kind of mind map exercises. In 2005, the team did a series of workshops, pastoralist interviews, field visits, pre-project sort of, before writing the proposals to the USAID, stakeholder workshop. This is a local vet going, oh my God, this is way more complicated than I ever thought it was. But this is one of these classic problems that's been studied, and the interventions that have been created have all been done piecemeal, right? So the folks interested in the park are working with the wildlife biologists and the veterinarians in the park, and they're just sort of focused on that piece of the problem. And the folks working on agriculture have got their agricultural economists and their the development specialists and the World Bank experts, and they're working on that part of the problem. And the people worried about, hydroelectricity are working on that problem. And then doctors are thinking about human health, and vets are thinking about animal health, and wildlife vets are thinking about. So it's like your classic problem of no one's talking to one another. So we came in and sort of decided that we were going to promote this kind of One Health perspective, and this kind of exercise was starting to look at those linkages of humans, wildlife, and livestock. And stepping back from it all and saying, we've been thinking about health interventions at the household scale or at the sort of village clinic scale. But what would a health intervention, a human health intervention, look like at the landscape scale? Right? What kinds of human health benefits could we get by thinking about the health of the landscape, in particular this before-after story of the drying of the river? So that generated this HALI Project, Health for Animals and Livelihood Improvement. We sometimes call it the One Health Project, and a vision for really thinking in a more transdisciplinary way about human and animal health. So, the results of that early brainstorming and data collection were to sort of realize a pretty substantial increase in recent times between livestock and horticulturalists in the area. Agriculturalists and the irrigation in particular versus the livestock keepers who are really at the bottom of the totem pole in terms of access to grazing resources and water holes and the health of their animals being driven more and more by water scarcity. Big increases in grazing pressure. It's way more complicated than just this regional story because a lot of the pastoralist tribes from the north have been kind of removed from the protected areas up there and were slowly making their way south. Tanzania still has laws that say, if you're a pastoralist and you come into town and there's some land, and you can have it. There's not a real strong kind of private property framework. It's really village land is common property, and pastoralists can come in and graze their animals. So we're seeing increasing grazing pressures in this area. Increasing wildlife conflicts and poaching in particular. So as you put pressure on people for food and for water, they're going to poach. And so we're certainly, in this context of the drying of the river and the pressures on people's livelihoods, seeing an increase in pressures on poaching. Maybe some evidence of decline in tourism revenues. I mean, this is not the Serengeti or Ngorongoro, but this is an area that's really been developing rapidly around tourism, and people don't like to see that in the lower right-hand corner. So, the collapse of these water-dependent species is a big deal for all of the money that's put into tourism development in that region, particularly this experiment around village-owned tourist operations. Pressures on wildlife, pressures on water and water quality, which impacts all of these things. We talked about the impacts on the national economy and the kind of increased blackouts that are happening because of the drying of the reservoirs. And one of the real understudied things is this emergence of new disease. And this is a population that already has major is immune compromised. The HIV/AIDS rate in that part of Tanzania is upwards of 15–18%. Co-infection with people between HIV and tuberculosis is upwards of 60%. So if you've got HIV, you tend to get TB. there's one of these re-emerging diseases, right? Like, oh, we thought we had TB under control. Along comes HIV, opens up the gate, now comes TB. TB is largely studied by medical doctors. Yet there's this bovine TB that sits over here that's largely studied by veterinarians. And that's the TB that you really get scared about because there's no antibiotics for that, there's antibiotic resistance for that, and all of a sudden you've got a new reservoir for a new emerging disease that could potentially be passed between people and humans, between humans and livestock that we're not even prepared for, and not even having that conversation. So that, out of these workshops, that became one of our focal emerging diseases that we were looking at was bovine tuberculosis. Also brucellosis, and a lot of diseases that are shared between people and livestock.
Is brucellosis like that?
Yeah, yeah. Sure. What's that?
Humans can get that?
Yeah, it's a zoonotic. It's usually between livestock and wildlife.
Yeah.
But there's fear of the transmission to humans as well. Yeah.
I heard a lot about that out in Montana and Buffalo
Yeah.
and all that, but I've never heard about the human connection.
Mm-hmm. So the HALI Project is born. It has these goals. Classic kind of science goals. Let's determine the prevalence and transmission ecology of the various zoonotic diseases. Brucellosis, tuberculosis, a bunch of waterborne diseases that we were interested in, crypto and all kinds of fun things. Among wildlife, livestock, and pastoral communities. Really sort of viewing these interfaces as ground zero for the emergence of new disease, right, and the emergence of old disease. Assess the effects of water management and quality on the presence, abundance, and severity of disease. So how is water and these larger landscape level processes, right, driving these disease interfaces is the big focus of this project. Assess how water management disease affect the health and economic livelihoods of pastoralists. So really trying to understand that component of that vicious circle, right? So you get the water management issue driving disease, driving pastoral livelihoods, and then you get more water management issues as people get desperate. Identify and recommend measures to mitigate the effects of zoonotic disease and water limitations, but in this more kind of transdisciplinary spirit. And a big goal of this is to strengthen local capacity to diagnose zoonotic disease. That's where a lot of the funding has gone, is to capacity development. How do we build capacity within the local veterinary community? How do we build bridges between these typically sequestered disciplines? And in humans, you talk to a doctor about zoonotic disease and they're like, and yet it's this sort of source, the big source of emerging disease. And so just that kind of capacity development, we decided early on we were going to do all the lab work in country, which is tough. You got to develop the capacity to do the lab work in country first. So a lot of the work has been gone into developing the diagnostic capacities at Sokoine, and also field capacity out in Ruaha, working with the national park to develop their disease monitoring capacity, training a whole slew of game scouts who work in that fringe area, a really important area between the park and the village lands, where sort of village-led hunting operations are happening, and training the game scouts to recognize disease and proper management of carcasses, working with the villages and the village government around sort of limiting some of the risk factors around drinking unpasteurized milk and drinking undercooked meat, and a big cultural one is drinking raw blood. And so these pastoralists have a tradition of especially the Maasai, in drinking blood from live animals. And so lots of things going on here that require some pretty intense capacity building. So the overall project ends up looking like this. We got people out doing livestock sampling. We're testing for TB in all the herds. Wildlife sampling, which has been the most difficult thing. To get permits to put your hands on a wildlife species is pretty tricky. Water sampling, so trying to connect the dots between, where are those hot spots on the landscape. where are those areas? And a lot of the transmission pathways through water aren't really known. It was never thought that you could get TB from water, and now we're not so sure. Those kinds of things. And then a lot of you know Michel Massazera. He does his PhD on developing the household survey, working with 160 households in the region, workshops in 21 villages, focus groups in the local town there with all of these diverse interests in mind. You know, all of this is sort of resulting in health and economic impact analysis of disease, recommendations for prevention, and a lot of this training and capacity building. But you know, this is the piece that's the hardest. And this is where Brian and Gary come in. Like, okay, guys, here's all this data from all these, like, smush it together and tell us what's going on here. That's the piece that we had the hardest time getting funded too. Like, we put that into the grant, and it was like they can understand this, and then when you talk to them about interdisciplinary, transdisciplinary ecosystem service modeling, they're like, oh God, that doesn't seem even possible. So we finally got it funded, because now we've got all of these studies. It's supposed to be a transdisciplinary project, but you got all these studies in their own journals and in their own masters and bachelors and all this sort of thing. Like, how do we pull these things together? So that was the focus of my sabbatical, the focus of this new funding that we've got from CRISP to do this kind of transdisciplinary disease modeling. I view the kind of work we're doing so far, and you can correct me if I'm wrong, Brian, as at the kind of scoping level. You know, scoping models have high generality, low resolution, but broad participation. So it's a pro-con kind of thing, right? We're getting really good participation. Brian and I held a modeling workshop at Sokoine University last May, was it? Sharing in data, trying to build those spatial databases. You know, a lot of data has been collected for years, and it's hidden away in different corners of government departments and studies and stuff. So that's been like a huge thing, is just using the goal of modeling to drive the acquisition of data and sort of create this interdisciplinary data set.
Excuse me, John, your last slide.
Yeah.
There's an intersection of two databases there. That's modeling?
It has been for us.
Okay, because, I mean, I guess what I would say
This is what I'm saying now. It's this development of an interdisciplinary database, right? Spatially explicit database that really connects the dots between. And then to get this to drive this, that requires models.
Okay. Then I'm kind of confused about the arrows that go directly from data to recommendations without analysis.
That's the sweet spot that I'm talking about. So the arrows aren't quite accurate how I'm drawing it, but it's the sweet spot of analyzing this data, and out pops the recommendations. Because all the recommendations have been at the household and village scale. We're trying to make landscape level recommendations to understand the sort of, if you will, the root causes of the disease processes, right?
Okay.
The water managers aren't thinking about disease. They're thinking about water and agriculture. The doc in the local clinic, he or she's not thinking about rice irrigation, why that's driving this new disease that all of a sudden we're seeing, right? The goal of this exercise is to bring all these folks together in some major aha moments. So, that's where we're at right now with scoping models. Research model is happening within each of these boxes. So there are people who have got their wildlife data and they're doing a research model, and people who've got their livestock data and are doing a research model. And the work we did with Michelle around all the socioeconomic data, we've got a conjoint model understanding these complex trade-offs. We're back a step trying to now bridge the gap between these various research models. And you know, I think that's the secret of what we try to do at Gond, right? Is not reinvent all of these individual wheels, but be the hub that brings them together. I don't know that we'll ever get here, but I mean, the goal of all this stuff is to have a management model eventually where you can run scenarios and ask a bunch of what-if questions and pull levers and turn dials and see what happens, right? That's where we'd like to get. I think our funding's a little bit too limited to get that far. And of course, as you go down the line here, you're increasing your complexity, your cost, your realism, your precision. It's not always worth it. I think Gary, a focus of your dissertation, right, on these trade-offs between resolution and scale, and how much time do you spend on these things?
Writing a paper on it right now.
All right. So here's the big brain dump on how we're trying to connect the dots. That's what I do. I connect dots. I know just enough about lots of things to be dangerous. So this is this classic kind of ecosystem services framework, right? That Ares is trying to do, that Natural Capital Project's trying to do, that Mines is trying to do. Here you've got a great story, right? Ecosystem source and sinks. You've got these upstream source waters, these wetlands that serves as a sink in the wet season and then a source in the dry season, and then these downstream sinks. If the extent of our analysis is just to stop at the reservoir and say, there's also this beneficiary of the reservoir for power. We're trying to understand these ecosystem service flow paths, right? So the delivery of water to the downstream wetlands from the streams and rivers to the main river and reservoirs. And so the limited amount of modeling we've done so far is just using the water supply model of Ares to try and scope that out, the delivery of water, and start to say some tentative things about where we might expect these disease hotspots to be. We're starting to get to this, we think. Ecosystem service flow disruptions, so you've got these upstream water withdrawals, you've got some tremendous land use pressures throughout the system, especially into the wetlands, although some of that's been relieved recently from the gazetting of that into the park. And all of these interactions along the way, right? And I think the big benefit for us to adopt Ares is it's very explicit about trying to model the flow of ecosystem services between sources and sinks, and from sources and sinks to actual beneficiaries. And we're really hyper-focused on these pastoralists, which have been the sort of least studied in the whole system. Yet they could be the most important, right, in terms of this disease interface, because they're on the front lines of these interactions between themselves, their livestock, and wildlife. So we've got all of these ecosystem service beneficiaries that we're worried about, from classic provisioning services like the food and fiber and water itself, to more of the regulating services. So, and there's trade-offs. How much water for rice versus water for downstream uses that could regulate disease processes, that could have benefits into the park and into the village economy, right? There's some of these trade-offs. So this is kind of the framework that's driving this research right now, is to understand these services in terms of providing for, right now we've really just looked at water supply. And then we've made some limited connections out to some epidemiology modeling around disease and some of these agent-based models around pastoralists and their movement. So if you stress them in one area, they're going to pick their cattle up and move to another, and they become a classic kind of disease interface and a movement of these disease processes across the landscape. And this is kind of back to your question, Bob. I mean, what we're trying to do is understand, are these sort of landscape level conservation initiatives, do they have these public health benefits? This is where I think a place like Gund could make tremendous impact, between classic studies that are happening around public health that are being funded by NIH in medical schools, ecosystem health kinds of studies that are being funded in environmental schools, all of the social sciences that are required to pull this together, from sociology to anthropology to economics. Well, who's doing the mixing and matching, right, and pulling these pieces of the puzzle together? So that's what we're trying to do through this ecosystem service modeling. From the headwaters type stuff, like if we improve ag efficiency, what does that get us? Wildlife management areas, wetlands protections, wetlands restoration, livestock management gains, in the pastoralist areas. Is there a place, so there's a lot of talk in Tanzania about sort of having the city folks fund the conservation and water initiatives upstream. They're the ultimate beneficiaries of the power. And then you've got an actual marketed instrument, power, at a few cents to everybody's power bill, right? And here comes this source of funds to do the kinds of restoration work that you need to do upstream. So just a few more slides. There's been a lot of work happening around these kinds of concepts, but we're trying to pull them all together. A group out of the UK, Langford and colleagues at SUA, have already really done the work of identifying the beneficiaries for us. You can think of the agricultural producers, the domestic users of water, the irrigated agriculture producers, the livestock producers, the benefits from tourism, the power producers, and then the urban power users, right? So it fits this classic kind of framework that is inside of a model like ARES. And then just a few maps to show some of the scoping work we've done to date. So you've got you've got your supply of water from rain. This is a really important aspect of this model, is the differences between dry season, wet season beneficiaries, and the seasonality of the main stem of the river. Overlaying that and trying to figure out possible surface water flows, so atmospheric, surface, and groundwater transitions. We haven't really done the groundwater piece yet, but would like to. And then you got to go through the hard work of figuring out evapotranspiration and infiltration into the water to figure out kind of what your sunk surface water flows are. Those of you who haven't seen ARES applications before, this is just your classic kind of progression from supply to demand, if you will. This then lets you sort of tease out, well, what's the actual surface water flow that we have to work with, and the actual sinks. So now thankfully the model's putting water into the river corridors, which is good. Now you start to, so that's sort of on the supply side. Now you start to figure out the demand side. Where are the populations? People. Well, this is all the protected areas, not a lot of people. You're seeing all of the population densities are largely around the road corridors. So trying to sort of model the interaction of where people are and their water needs. So now you start to overlay land cover, land use type data, particularly to tease out the agricultural water needs and the location of the village centers and households. And we've got 160 households who we work very closely with, where we can start to get a little bit more detailed on the water demand and the impacts of water restrictions. Estimates of ag surface water use. Okay, so these are all those highland areas. This is where a lot of those irrigation projects are. We've got the maps now for irrigation, but we haven't put those in yet. Yeah, so we even know where the big irrigation projects are. What's cool about ARES, which a lot of other models are trying to do, but I think ARES is the only one that's really getting somewhere, is to map uncertainty as well. Mm-hmm. So a lot of the ecosystem service models are parameterized, and you're just looking to sort of come up with some kind of estimate for point estimate for a particular parameter and a particular physical relationship, without really understanding the uncertainty around those parameters. Because ARES is more probabilistic in nature, and when we don't have good data, we use these Bayesian networks, these belief networks, to really populate the model with probability estimates of the different parameters, not just point estimates. Mm-hmm. Then we can map uncertainty, which is really cool.
Actually, every map he's shown you so far has an associated uncertainty layer. So the maps he's shown you are actually the mean values in each pixel, because every pixel on every one of those maps has a distribution inside it. So he's showing you the means, and then this is a variance map, actually, per pixel. So it's just showing the other side of the coin, just a different way of viewing.
I'm not giving you a legend on any of these.
Yeah, so what actually are the colors? Is it agricultural surface? The one before?
This one, the darker is less uncertainty, and the lighter, which is actually up in the protected areas.
But is it a percentage of use? I mean, what do you mean by surface water use? Is it?
So what Gary said, there's a range of surface water use, and this is showing the means.
It's in millimeters.
Okay.
Yeah, the units would be, it's a point density. So, so it's millimeters of water essentially averaged over the cell. So if you take the size of the cell in kilometers squared or whatever the unit is, multiplied by millimeters in height, which would be the value in this, you get volume of water, which is the assumed, or which is the estimate for consumption in a year.
Is it based on the crop that's there, or what?
It's based on the land cover type, so this is showing where there's actual
Back to the
agricultural.
land cover.
Okay, so just
Agricultural
agriculture
production.
gets one blanket, use.
We're trying to
Or
tease out the
volume.
different types of agriculture.
Cool.
The more information we have about the types of crops being produced in a place, then
Yeah.
the more we could distinguish between the water demands in a specific location. Right now, what we have from the land cover data is
Ag.
agricultural.
Right,
So without more information, all we can say is, here's a general estimate of a per volume estimate for each pixel of agriculture on an annual demand for water.
Right now, the water demanders that are modeled are households, planted agriculture, and then also livestock. So, but it's at that scoping stage.
How much water is needed for agriculture in this area per year over this area the size of a pixel? Then instead of giving it a value, give it a distribution of value, right? Saying, well, I don't know what the crop is, so here's an estimate. Here's a distribution of what the values might be with associated uncertainties based on, for example, the frequency of the crops that you have in the area. If you don't have information about, the relative placement of crops, then you have to kind of go with a more uniform distribution, and so on and so forth. But that's the kind of information we plug in. So there's a distribution in each pixel over the expected volume. Then you run the simulation to see how much water actually can get there. Distribution again because the input is uncertain. And then you say, so this is the possible, estimate of how much water might arrive at this agriculture, and then you look at sort of the difference between those two, and you're doing probabilistic arithmetic, right? What's the random variable x minus the random variable y, kind of things, a new distribution over some states, yada, yada, yada. But so ultimately you get a new distribution saying how much water is left over that makes it out of this pixel, distribution of how much water makes it out of the pixel, not just this is the volume, but a distribution of volumes, and so on and so forth, all the way down. So every calculation in the entire system for the whole simulation is probabilistic, and every stage of the way you get distributions anywhere you want. You can aggregate them in a lot of ways.
And that's another big advantage of this. This model moves water, and there's been other models that have been done in the area, like the WASI model, which just is simply trying to understand the availability of water in watersheds, but doesn't move water and doesn't match the availability with the demanders. So the real secret here is to try to move water, and then also sort of try to understand. Now I want to get to my last one. I've only got a couple more slides, and then these are the details that I promised you at the beginning of the talk that I would just glaze over. Okay? I should have set some boundaries.
The first map that you put up said precipitation,
Yeah.
but was it in the north was high precipitation, or in the south is high precipitation?
The green is high values, the red
So
is
the green is the high, okay.
Yeah, so these are the highlands that the storm systems are coming through generally in this direction, and this really, the highlands are capturing a lot of that precipitation, yeah. And then so when the development folks came through in the 70s, and all of this was completely undeveloped, just wild areas and some pastureless really, they said, wow, we got a lot of water, let's do rice. And so then the rice irrigation projects came in the highlands.
What's the elevation?
Oh, God. 3,000 feet, maybe, I'm guessing. I forget.
In the valley or the peaks?
Up here in the highlands.
Okay.
Yeah. No, let me think. Oringa is more like higher than that.
Oringa is like 5,000 feet.
It's 5,000 feet, right? Oringa, which is farther down.
Yeah.
Yeah. So maybe 6,000 or 7,000 feet in the highlands, and then 2,000 to 3,000 feet downstream. But what we're trying to get to, and to connect then back out to the health story of interfaces, right, is, so 2 more maps. Now you start to get at where your surface water demand is the greatest, and we're still trying to work this out because we have so many, maybe this is true, this was the first areas that was this many pixels, right?
Oh yeah, sure. For
lot
use,
of
we
frequency.
just follow the high number.
population.
Yeah, so we think this is accurate. We're just showing the real high demanders here in this
0.5%.
one. There's many more water demanders in the landscape, but we're carving out the real high ones. And what we're starting to get to is this notion of where is there a blockage, right? Where are we seeing a disconnect between supply and demand in the simplest terms? So this map is starting to show you where you might see pressure points, if you will, where this water stress between supply and demand is the highest.
Yeah, this is actually, so this is a subset of the previous map.
Yep.
So if you show the previous map again. Okay, so this is the top 6.5% water users, right? Just the very top, to
Yep.
pick it out so it's an easier map to see. If you go to
But
the
this
next
is
map,
just demand, the next one couples it with
that's where the users
supply.
are, right? So then this one is showing you, so that's saying where we expect that the demand is a distribution for each of those locations. This is showing you the pixels are in the same place, okay? The values have been reduced.
Yeah.
This is saying how much water do we think was lost to each one of those users, which are the green pixels, and the degree to which they're green. The coloration is indicating the amount of water that they lost upstream sinks, right? So that's the amount of water each user lost that could be remedied by addressing sinks upstream in the system. So that's what this is trying to show. But obviously it's only showing net loss to the top 6.5% of users. So some of them didn't lose anything to upstream sinks, which is why they disappeared from the map, and some of them lost more than others. So that's what's going on with this kind of thing. It's just
When you lost, it didn't make it to them because it
Yeah,
was
'cause-
stopped somewhere or
exactly.
in a sink or.
Yes, because this is it's like unmet demand.
Yeah. And so what ARIS tries to accomplish is modeling sources of delivery of ecosystem service. In this case, we're just looking at water supply. There's flow paths from the supply to demanders. Sometimes these demanders, it's non-rival demand, so or it's partially rival. They use some of it, but the rest goes away. Or if it's rival, it's gone, right? If it's completely rival. And then there are some folks that aren't connected by these pathways at all. So this is the real unmet demand. What we're trying to get at with this kind of analysis is sort of identify, in my simplistic terms, like where are those stress points?
Yeah, these are people who are on flow paths.
They're on flow
They're on
paths.
flow paths, but
But they're not
because
getting
of
what they'd
the
like.
configuration upstream, they've lost something
Yeah.
that they could get if those things were reduced. There's actually a series of maps here that show each of those different components.
So you can imagine, this is what I'm sort of saying blockage, right? You can
Yeah.
imagine that somehow the flow path from supply to demand is getting blocked.
There's a sink there, like somebody did a withdrawal,
Yep.
something like the rival use thing.
That guy came in and.
So now we're at this sort of 10,000 foot scale, thinking about the dynamics of the landscape, right? Now there's all these beneficiaries dotted around the landscape. And now we're starting to identify, we think, and now this has to be married with some of the epidemiology modeling that's happening at UC Davis. We're starting to identify where these kinds of hotspots would be in terms of water stress. Water stress is leading to disease, magnified disease processes. In our case, at this interface between people, livestock, and wildlife.
There's a water problem. There ain't enough water. That's true in many places in the world. We're hearing that increasingly. The second is there's a disease problem, which water plays a big part in.
Yeah.
And if you're truly running out of water, it seems to me that that's an easier problem to deal with. There's efficiency of use, and then there's shipping it in by truck from Vermont. But the disease thing, I guess I put it this way: are there examples of disease community health interventions around in the world that are indicative of the kind that might be used here? I know I don't want to say if it was used in Florida, it should be used in Tanzania, but some of them seem to be just like adjusting water levels, keeping folks out of certain areas at certain times, and so on. So I made 2 points. One is that the water thing and the disease thing, although I understand they're coupled to some extent,
Yep.
I see a separation. And second, even though you haven't done the modeling yet, do you have some sense of the kinds of recommendations you would make?
Yeah, so on the side of the study where we're doing surveys at the household level, we're doing sampling of disease in livestock, the UC Davis team just got funding from NIH now to do sampling amongst humans as well, which that's been a limiting piece for us. Is sort of, we've got data on reported health problems, but we don't actually know what people are getting. Three sort of main points of intervention emerge at the household scale, for example. And then what we're trying to understand in our team is the points of intervention at the landscape scale. and how they interact. At the household scale, you've got people living in close proximity with their animals, okay? And traditionally, folks build bomas, so these livestock enclosures, and they put their houses inside the livestock enclosures. Depends on the tribe. Some do and some don't. So that's a risk factor that's been part of these dialogues at the village scale. Eating untreated, unpasteurized milk or undercooked meat, so there's some classic, that's another point of intervention. Drinking raw blood is another point of intervention. A big one that connects back to the water is just simply the sharing of water resources. So what we've done in our water sampling protocol is we've sampled water that's used just by humans, water that's used by humans and livestock, and then water that's really being hammered by humans, livestock, and wildlife, and trying to tease out the epidemiology behind disease transmission and those kinds of hotspots. People are creatures of habit, and they use water resources because they're easy to use. And we've surveyed people on what they think the source of disease is in their households, and more than half say they don't know, and then others say, well, from God or from my neighbor, or very few say the environment, or sometimes there's some answers that sound like the environment, like from flies. So these become these points of intervention because people ultimately are at these interfaces, right? And they're making decisions that modify behavioral decisions at these interfaces. So a big chunk of the next round of funding is to do the outreach education. We've done some now through radio shows, through skits and stuff, and we did a big thing on Rabies Day a couple years ago in the villages. We showed a movie and talked about zoonotic disease. Just the perception of, are you able to get disease from animals or from water, and breaking down those barriers has been a big part of this.
Right, so just because it's new,
Yeah.
so we'll have you finish your talk and then we'll do questions.
So I'm done, so we can just.
Oh, okay, sorry, I wasn't sure you said you had more slides.
No, this is the last one.
Okay.
So I'm still pushing you just for one typical example intervention that might come out of this. Is it one thing, like maintaining the water level of a wetland in certain bounds for a certain time?
So this is providing, and so there's a lot of discussion that's happening right now, and our team's part of it, around what would minimum dry season flows look like, and who would benefit from them. If we can get that number, minimum dry season flows, right? Then we can put the pressure on, for example, upstream. What's happening right now is laws are being created to say no more dry season irrigation, or only limited dry season irrigation, or the agricultural colleagues at Sokoine University are working on simply water use efficiency, especially in the dry season. A lot of this is being driven by the WWFs and the WCS that are worried about hydrological flows for animal populations.
Okay, yeah.
We're bringing in the public health dimension. It's one more sort of, arrow in the arsenal that's saying there are huge public demands beyond just growing more rice in the desert.
Absolutely, that's fine, I'm happy.
Yeah. So our thinking has been at that landscape intervention level. A lot of the extension thinking, and a lot of our colleagues at WCS and at Wildlife Health Center and at Sokoine University are also thinking at the household level intervention, which are just as important, but ultimately just become the kind of, you're always just trying to kind of keep up when you're not dealing with the root causes of the problems, which if water is driving these disease vectors, then let's go upstream and talk about water. There's been zero conversation about health beneficiaries to better water management. Now we've opened up that conversation. So thanks for your questions and your time.
Thanks, Jon.